Hey everyone, welcome back. Here's something to think about. Have you ever poured yourself a cup of tea, got distracted, and by the time you returned, it was no longer steaming hot? Or noticed that soup cools quickly at first, but then takes forever to reach room temperature? That's not just your bad timing, that's Newton's law of cooling in action. When a hot object, say a cup of coffee, is left in cooler air, it loses heat and gradually cools down until it reaches the same temperature as the surroundings. The rate of cooling depends on how big the temperature gap is between the object and its environment. When that difference is large, cooling happens quickly. But as the object's temperature gets closer to the surrounding temperature, cooling slows down. If we plot a graph of temperature versus time, we'll see a steep curve at first that slowly flattens out. That's our cooling curve. So the next time your coffee goes cold too soon, don't blame your luck, blame physics. It's literally doing exactly what Newton predicted centuries ago. Now, let's bring Sir Isaac Newton back, not the Apple one this time, but the scientist who also figured out how hot objects cool down. He observed that when the temperature difference between a body and its surroundings is small, say less than 30 degrees Celsius, the rate of cooling is directly proportional to that temperature difference. Mathematically, it's written as negative dq by dt equals k multiplied by open bracket t sub 2 minus t sub 1 close bracket. Let's decode that. The symbol dq by dt is the rate at which heat is lost in joules per second. The constant k depends on the body's surface, the medium around it, and other conditions. T sub 2 is the temperature of the object, and T sub 1 is the temperature of the surroundings. Think of a hot pizza slice left in an air-conditioned room. When it's fresh from the oven, let's say 200 degrees Celsius, it cools down quickly. But once it reaches around 40 degrees Celsius, it cools much slower. The temperature difference shrinks, and so does the rate of cooling. That's Newton's law of cooling at work, deliciously. Alright, time to turn up the math, but don't worry, this is the fun kind of physics math. Let's say we have a body of mass m and specific heat capacity S cooling from temperature T sub 2 to T sub 1. The small amount of heat it loses in time interval dt is given by dq equals m multiplied by s multiplied by dt sub 2. Now, Newton's law says that the rate of heat loss is proportional to the temperature difference. So we can write negative m multiplied by s multiplied by dt sub 2 by dt equals k multiplied by open bracket t sub 2 minus t sub 1 close bracket. If we rearrange and integrate, we get natural log of open bracket t sub 2 minus t sub 1 close bracket equals negative k multiplied by t plus c, where capital K equals k divided by open bracket m multiplied by s close bracket. This equation shows that the temperature difference decreases exponentially with time. That means it drops rapidly at first, then slows down over time. As shown in the cooling curve, the steep part represents fast cooling, while the flat part near the end shows slow cooling. That's the exponential decay in action. So even your morning tea is secretly solving an exponential equation while it cools. Physics never rests. Now, how do scientists prove Newton's law of cooling in the lab? Let's find out. If you plot the natural logarithm of the temperature difference, that's ln of open bracket t sub 2 minus t sub 1 close bracket against time, you get a straight line. The equation we derived earlier, ln of open bracket t sub 2 minus t sub 1 close bracket equals negative k multiplied by t plus c, predicts this perfectly. The slope of that line is negative k, and that slope gives us the cooling rate. Experimentally, we use a double-walled calorimeter filled with hot water. The outer wall minimizes heat losses to the air, and a thermometer measures how the temperature changes over time. When we plot the data, the straight line graph confirms the law. The steeper the slope, the faster the body loses heat, meaning a larger K value. It's like melting ice cream outside on a sunny day. The slope is steep, but in your refrigerator, it's almost flat. Same physics, different surroundings. Now, let's make this practical with an example, and this one's tasty. Imagine you've just taken a hot pan of soup off the stove. It cools from 94 degrees Celsius to 86 degrees Celsius in 2 minutes. The room temperature is 20 degrees Celsius. We want to find how long it takes to cool from 71 degrees Celsius to 69 degrees Celsius. For small temperature differences, we can use the proportional relation. Change in temperature 1 divided by open bracket time 1 multiplied by average temperature 1 close bracket equals change in temperature 2 divided by open bracket time 2 multiplied by average temperature 2 close bracket. Substituting the numbers, 8 divided by open bracket 2 multiplied by 70 close bracket equals 2 divided by open bracket T2 multiplied by 50 close bracket. Solving this gives T2 equals 0.7 minutes, which is about 42 seconds. So, our hot soup takes around 42 seconds to cool those last 2 degrees. Notice how it cools more slowly now because it's much closer to room temperature. That's the beauty of Newton's law. It predicts the slowing down of cooling perfectly. So yes, physics can even tell you when your food is ready to eat, no thermometer needed. Alright, let's wrap things up before our brains and our coffee cool off completely. Newton's law of cooling tells us that the rate of cooling of a body is directly proportional to the temperature difference between the body and its surroundings, but only when that difference is small. It also tells us that temperature doesn't drop at a constant rate, it decreases exponentially, fast at first, then slowly as equilibrium approaches. This law explains so many everyday things. How a cup of tea cools, how buildings lose heat at night, why car radiators work efficiently, and even how forensic scientists estimate time of death by measuring body cooling. So, next time you blow on your noodles to cool them faster, just remember, you're not just hungry, you're conducting a practical demonstration of Newton's law of cooling. How's that for hot physics? I hope you enjoyed this cool journey through thermal physics. Stay curious, stay caffeinated, and I'll see you in the next session where physics heats up again.